In today's video, we will look at the derivative as a rate of change. Now, you should recall that if we're given the interval x to x plus h, then the average rate of change of a function f of x, obviously h greater than 0, is given by delta f average x plus h, f of x plus h minus f of x all over x plus h minus x. So this is f of x plus h minus f of x all over h. However, this is the slope of a secant line. Now, this is just an average rate of change over an interval. What if we want an instantaneous rate of change at x? Well, instantaneous rate of change, just pass this through the limit as h goes to 0. So instantaneous rate of change is the limit as h goes to 0 of delta f average. However, that is the definition of a derivative. So we say that the instantaneous rate of change, that is, the rate of change at that instant, of a function f of x at a value a is f prime of a. It is the derivative of f at a. Now let's consider an object that is in motion. Now we're only going to consider one-dimensional motion here, so it's moving along a straight line. Multi-dimensional motion will be studied in Calculus 3. Now, we can represent the object's path as s of t, a function of t. So this is the position at time t. The velocity of the object, represented v of t, is the rate of change of position with respect to time. So it is s prime of t. Acceleration of the object, represented a of t, is the change of velocity with respect to time. So it is v prime of t. But notice that is also s double prime of t. So it's the second derivative of position. Then we also have the speed of the object. This is just simply represented as the absolute value of its velocity. Okay. Now, Galileo had discovered that the height, represented y of t, of an object tossed vertically in the air near the Earth's surface is accurately represented by this function. Y of t is equal to y naught plus v naught t minus 1/2 gt squared. In this case, y naught is the initial height of the object. V naught is the initial velocity of the object. And g is the acceleration that is due to gravity near the Earth's surface, and we take it to be approximately 9.8 meters per second or 32 feet per second per second. Now, an object that's following this model is said to be in free fall. Physics is not the only field in which rates of change appear. Rates of change appear everywhere. One of the most common non-physics examples is in economics. This has to deal with the idea of marginal cost, marginal profit, and marginal revenue. So if we let c of x represent the cost function for producing x units, then the marginal cost is given by dc dx. It's the derivative of the cost function with respect to x. And what this represents is an approximate change in cost for producing the x plus 1 unit. In other words, when you're already producing x units, the marginal cost gives an estimate for how much it would cost to produce the next unit. Now, r of x is revenue function for producing x units. The marginal revenue is given by dr dx. It's the derivative of revenue with respect to x. And this is an approximate change in revenue for selling the x plus 1 unit. Now, so when you're already selling x units, marginal revenue gives you an approximate extra revenue, either positive or negative, right? So either gain in revenue or loss in revenue for selling that x plus first unit. And finally, p of x represents the profit function for selling x units. I'm sorry, p where it's in r of x, that should have been selling, not producing. Now, profit is how much money you bring in, the revenue, minus how much it cost. Marginal profit is, as you should be able to guess, dp dx, the chain or the derivative of the profit function. And this is an approximate change in profit for producing and selling the x plus 1 unit. So when you're already producing and selling x units, marginal profit will give an approximate change in profit, either gain in profit or loss in profit, for both producing and selling the very next unit. We will now conclude by looking at several examples. So for our first example, let's look here. A ball is dropped from a height of 64 feet. Its height above ground, measured in feet, t seconds later is given by s of t equals negative 16t squared plus 64. We want to determine instantaneous velocity of the ball when it hits the ground. So what is the velocity the instant the ball hits the ground? And then what is the average velocity during this fall? for part A, since we're looking for instantaneous velocity, we want v of t, which is s prime of t. So this will be negative 32t, and then derivative of 64 is 0. Now to determine when it hits the ground, we want to solve s of t equals 0. Right? Because ground level would be a height of 0. We can divide by that negative 16. We'll be left with t squared minus 4 is equal to 0. And from here we get t is either plus or minus 2. However, time has to be non-negative. So we take time equals 2. So it takes 2 seconds to hit the ground. We now just find v of 2, which is negative 64, and the units are feet per second. So the instant the ball hits the ground, it is traveling 64 feet per second in a downwards direction. That's what the negative indicates. Now for the average velocity, call it v average, this will just be s of 2 minus s of 0 over 2 minus 0. S of 2 is 0, obviously, we solved that already. S of 0 is 64, all divided by 2, we get negative 32 feet per second as our average velocity over this fall. Let us now consider this example. Position of a particle moving along a coordinate axis is given by that function. We want to find v of t, determine the time or times the particle is at rest, and then determine over what time intervals it's moving from left to right, and then from right to left. All right. So find v, that is just s prime 3t squared minus 18t plus 24. Now determine times that it's at rest. Well, if it's at rest, that means the particle has 0 velocity. So we want to solve v of t equals 0. We can divide by that 3. T squared minus 6t plus 8 equals 0. That can be factored down to t minus 2 times t minus 4. And so we get that the particle's at rest at 2 seconds and at 4 seconds. To determine intervals, by convention, moving left to right is positive, moving right to left is negative. So we want to determine intervals on which velocity is positive versus negative. So let's create a chart. So this function here is called the sine function, not the trigonometric sine, but sine as in positive or negative. So if v of t is less than 0, it'll spit out a negative. If v of t is greater than 0, it'll spit out positive. Well, over the first interval, remember, time has to be non-negative, so it starts at 0. So from the time 0 to when it is at rest, what is the sign of velocity? So we pick a number, pick 1, plug it into v of t. Right, so we'll get 3 minus 18 plus 24. Right, so 27 is definitely greater than 18, so that is positive. Now, from 2 to 4, right, so it starts moving again after 2 seconds. It's at rest again at 4 seconds. 3, so we get 3 times 27 plus 24 minus 3 times 18. That should give you negative. And then 4 until the rest of time, right? It's going to keep moving then forever. 5, if you plug 5 in to V, you should find that it is positive. So, particle moves left to right from 0 to 2 seconds, and then again 4 onwards. It moves right to left over the interval 2 to 4 seconds. Now let's consider this problem. Find the acceleration of a ball tossed vertically in the air from ground level with an initial velocity of 12 meters per second. Right. So S naught would be 0 meters. V naught is 12 meters per second. Right, so this means that S of t, 12t minus 1/2 gt squared. V of t would be 12 minus gt. A of t, which is the derivative of velocity, is just negative g. Right, so what this is saying is that the acceleration is only the acceleration due to gravity. So it's negative 9.8 meters per second per second. And in fact, this is true. It does not matter what the initial position is, what the initial height is. If it's in free fall, the only acceleration on the object is that due to gravity, which is a constant negative 9.8 meters per second per second. And finally, let's consider this example. This has to deal with economics. So barbecue dinners that can be sold is represented by X, related to the price changed or price charged by the equation P of X equals 9 minus 0.03X for X between 0 and 300. We wish to determine the revenue function and use marginal revenue to estimate the revenue obtained from selling the 101st barbecue dinner and compare this to the actual revenue that is obtained. So revenue, how much money you bring in would be how many units you sell times the price per unit. So R of X is X times P of X. So X times 9 minus 0.03X, which is 9X minus 0.03X squared. We now wish to find marginal revenue. That is just R prime of X. So 9 minus 0.06X. That is our marginal revenue. To find an estimate of the revenue obtained from selling the 101st, we just do R prime of 100. Right? Remember, R prime of X is an estimate for the amount of revenue we gain from the X plus 1 unit. We get 9 minus 0.06 times 100. It's 9 minus 6, which is $3. So we estimate that the 101st barbecue dinner will bring in an extra $3. To find the actual revenue, what we want is R of 101 minus R of 100. All right, so R of 101, remember revenue is 9x minus that 0.03x squared. This gives 602.97. R of 100 is 600. So the actual extra revenue from selling the 101st barbecue dinner would be $2.97. So you can see that this R prime is a really, really good estimate. With that, that concludes this video. In the next video, we will be looking at how to find the slope of a function that is implicitly defined.